Welcome to the Explainer. Have you ever noticed your phone getting warm when it's working hard? Or just wondered why no machine ever is 100% perfect? Well, today we are diving right into that. We're going to tackle the fundamental inefficiency of, well, everything. We'll explore why every single system wastes energy and then look at the really clever ways engineers are fighting back against that basic law of physics to save energy and, of course, a whole lot of money.
So here's what we're going to cover. First, we'll unpack the core problem of inefficiency itself. Then, we'll figure out what a perfect machine would even look like, and how we grade real ones against it. After that, we'll get into some seriously smart engineering tricks, before we wrap it all up with a real-world example of just how expensive a tiny bit of waste can be. Okay, so let's get into the big puzzle. The number one reason no machine can ever be perfect is because of something engineers call irreversibilities. You can think of them like tiny little energy thieves that exist in every real-world process. They're unavoidable imperfections that just add up and drag down the performance of any system. I mean, think about it, right? Nothing can move without at least a little bit of friction. No water or air flows perfectly smoothly. There's always some chaotic turbulence. And pretty much any process that uses energy is going to lose some of that as heat to the world around it. It's just how things work. So if a truly perfect, 100% efficient machine is impossible, how in the world do engineers even know what they're aiming for?
Well, that's where you get clever. You have to create a theoretical gold standard. Engineers essentially build an ideal, imaginary machine, on paper, of course. This perfect model serves as the ultimate benchmark, the top score that all our real, messy, everyday devices are trying to hit.
And this idealized concept, this is a big one. It's called reversible work. It's basically the perfect world scenario. It represents the absolute maximum work you could ever hope to get out of a turbine, or the absolute minimum work you'd need to run a compressor. It's a totally frictionless, perfectly balanced process that, yeah, is impossible in reality, but it gives engineers a concrete target to shoot for.
Now, how we calculate this ideal work depends on the system, and the difference in the math looks tiny, but it's absolutely critical. For a closed system, like a simple piston, work depends on pressure changes over volume. But for a steady flow device, like a turbine or a compressor, the equation basically flips. And that little v, the specific volume, you're going to see in a second. That is the key to everything.
So this brings us to the most important part. Specific volume is really just how much space a certain amount of a substance takes up. You know, a gas has a way, way larger specific volume than a liquid. And here's the kicker. The larger that V is, the more work it takes to compress something. This one single variable has enormous consequences for how we design things. And wow, just look at what this means in practice. Let's say we want to compress water between two pressures. When it's a liquid, compressing it takes less than 1 kilojoule of work. But if we try to compress that exact same substance, H2O, as steam, the work required explodes to almost 520 kilojoules. The difference is it's staggering. I mean, that's over 500 times more work just to compress the vapor. It's the same stuff, the same pressure change, but the enormous specific volume of the steam just sends that energy cost through the roof. This, right here, is exactly why power plants go to such great lengths to condense steam back into a liquid before they try to pump it.
Okay, so we've got our perfect world benchmark. The next obvious question is, how do our real, imperfect machines actually measure up? How do we grade them and create a kind of efficiency scorecard?
We do it with a concept called isentropic efficiency. Now, in a perfect, heat-contained device, the process would be isentropic. That's the ideal, with zero friction, zero heat loss. The actual process, of course, is messy. It's got all those things. So isentropic efficiency is really just a grade, a score that tells us exactly how close our real machine gets to that perfect version. For a turbine, the goal is to get the most work out, right? So the efficiency score is pretty simple. It's the actual work you get divided by the ideal work you could have gotten. Since reality is never perfect, the actual is always a little less, so the score is always under 100%. And just to give you a feel for it, some of the big, really well-designed steam turbines, they can hit over 90% efficiency.
That's pretty amazing.
Now, for a compressor, the goal is the complete opposite. We want to use the least amount of work possible to get the job done. But the actual work we have to put in is always more than the ideal. So to keep the score making sense, under 100%, we just flip the fraction. The ideal work goes on top. Good compressors are often in that 80 to 90% efficiency range.
Okay, so we know how to keep score. Now for the fun part. How do we actually improve the score? How do engineers get these devices to perform closer to that perfect, ideal benchmark we've been talking about? All right, let's go back to that key idea, specific volume. For a gas, temperature and specific volume are totally connected. If you can cool a gas down, it gets denser, and its specific volume shrinks right up. And like we said, a smaller V means less work is needed to compress it. So all of a sudden, cooling becomes a super important strategy.
And this chart just lays it out perfectly. That first bar, the isentropic case, that's our baseline with no cooling at all. Takes about 263 kilojoules. Then look at the middle bar. We add some cooling to the process and the work drops. And that last bar, that's where we go all out and cool it enough to keep the temperature steady. And wow, the work plummets to just 189 kilojoules. The takeaway is simple. The more you cool, the more energy you save.
But how do you actually cool a gas while you're trying to compress it? Well, one of the most common and smartest tricks is to do it in stages. First, you compress the gas a little bit. Then you hit pause, and you run it through this device called an intercooler, which is basically just a radiator to cool it way down. Now the gas is cooler and denser, so that second round of compression is way, way easier. It's a brilliant trick that saves a ton of energy.
All right, so we've been deep in the engineering weeds. Let's pull back up for a second. Because this isn't just about formulas on a whiteboard. This stuff translates directly into cold, hard cash. Just think about this for a second. In most factories and manufacturing plants, compressed air is so critical, they actually call it the fourth utility. But unlike turning on the tap for water, it's not free. Not by a long shot. Making that compressed air is a huge operational expense.
How expensive? Just look at this number. A single medium-sized industrial compressor can burn through more than $50,000 in electricity every single year. I mean, think about that. That's often more than what the machine itself cost to buy in the first place.
And here is where inefficiency really, really hits the wallet. All of that money, all of that expensive energy you spent to compress the air, it's completely and utterly wasted if that air just hisses out of a leaky pipe somewhere. It's wild. Some studies have shown that certain facilities can lose up to 40% of their compressed air just to leaks. That's like throwing away 4 out of every $10 you spend. So what does all that boil down to for just one tiny little leak? Using the principles we just talked about, we can actually calculate the cost. A single hole, just 3 millimeters wide, that's smaller than a pea, just hissing away in a forgotten corner of a factory, can waste over $900 a year. $900 from one tiny little hole.
So let's tie it all together. We saw that while no machine can ever be perfect, engineers are clever. They use these ideal benchmarks, these isentropic processes, to grade them. They figured out that specific volume is a key weakness to attack, so they use tricks like cooling and staging to close that efficiency gap. And as we just saw, this isn't just theory. Every bit of that saved energy has a real, measurable financial benefit. And this whole journey, from abstract formulas all the way down to a $900 air leak, it kind of leaves us with one final thought. In a world that runs on energy, what are the invisible inefficiencies, the hidden leaks in your world that are quietly costing you energy and money every single day?